Recall that we've been finding the interval of convergence for a power series. And we've been doing this by identifying the center, identifying what we know about the radius, and then checking the endpoints. We're using a lot of the stuff from the ratio test, including the hierarchy of types of factors. Sitting at the top are your factorial factors. In the middle, you've got your exponential factors, and down at the bottom, beneath the notice of the ratio test, are your rational and radical factors. Your rational and radical factors will just be what you use to determine what's going on at the endpoints. Your exponential factors will help you determine what the positive finite radius of convergence is. And your factorial factors are when you're going to suspect that there will be an infinite radius of convergence or a zero radius of convergence. So one way to think about this hierarchy is that we're also thinking numerator versus denominator. We're thinking numerator versus denominator. So far, we've been doing examples where the type of factor just appears in one location, the numerator versus the denominator. So if we have an exponential factor in the denominator and also in the numerator, we want to balance those out. The same thing can happen with factorials. If there's a factorial in the denominator, it might be balanced out by some other factorial in the numerator. But this is our general hierarchy. At the bottom is your rational, just affect the endpoints. This is the weakest way we put together numbers in this fashion, very large numbers. We're just taking a very large number to a fixed base. Exponential will reverse those roles. We're taking a fixed base and raising it to an increasingly large number. And in a factorial, we're kind of doing both. We're increasing the number of factors and the factors themselves are getting bigger. So the base gets bigger along with the exponent. I know that factorials don't have to have exponents in them, but if we think of exponents as just be the number of factors. Factorials have an increasing number of factors, but the base, the factors themselves are getting bigger. In an exponential, we're having an increasing number of factors, but the factors are all the same. So that's how we can think about our hierarchy of power when it comes to the ratio test. All right. So looking at this example here, I've got an n+4 cubed. That's a rational part. That's only going to affect the endpoints. You notice that this rational part, n third, n cubed, that's in the numerator. That means at the endpoints, we're going to have an n cubed or an alternating n cubed. So this tells us that the endpoints are out. We are not going to be worried about the endpoints. The x minus 2 to the n tells us that the center of this series is at 2. And 10 to the n in the denominator, that's an exponential factor, tells us that the radius of convergence will be 10. So this is just how we read what's going on here. The n+4 cubed, that's rational. It's telling us that the endpoints are not included in our interval of convergence. The x minus 2 to the n, and this is telling us that the center is at 2. And a 10 to the n in the denominator is telling us that the radius is going to be 10. So if we go to draw our interval of convergence, our center is going to be at 2. Our radius is 10. So we'll go 2 plus 10 is 12. 2 minus 10 is -8. Since the n plus n cubed is going to be in the numerator, one endpoint will be an alternating n cubed, which diverges. The other endpoints will be just an n cubed, which diverges. So at both endpoints, we have divergence, but then we have convergence all throughout the middle. We want to be able to identify all these pieces without having to resort to using the ratio test. We don't want to write down the ratio test. We just want to know what's going to happen with the ratio test. In interval notation, we would say this is the interval from -8 to 12, with both endpoints excluded. This is all the x strictly between -8 and 12. Since the endpoints are doing the same thing, we have the same inequality all throughout our compound inequality. We could say this is the absolute value of x minus 2 is strictly less than 10, everything within 10 units of 2. The reason I want to write down the absolute value inequality as often as we do is that this is an important construction. We need to be able to read this as everything within 10 units of 2. The first time we see this kind of absolute value inequality is back in an algebra class, but it's kind of removed from any kind of context why we would care about everything within 10 units of 2. And we're focused on rewriting our absolute value inequality in this format as a compound inequality. Because someone said, because first of all, it's a mechanical thing that you can do. And second of all, it illustrates very clearly what we're saying when we write this down. Everything within 10 units of 2. That would be everything between -8 and 12. And so the point of those exercises back in the day, back in the halcyon days of algebra when everything was so simple, was to make this connection. To make the connection that the absolute value of x minus 2 less than 10 means that x is between -8 and 12, because that is everything within 10 units of 2. That's an important part of the reading exercise here. Everything within 10 units of 2. And since it's less than and not less than or equal to, it's everything strictly within 10 units, strictly within 10 units of 2. So not including -8 and not including the 12. Moreover, you want to be able to move things around. So if we have other things to balance out, if there was another exponential factor running around, like for example, we'll have another factor. 4 showed up twice. A lot of this stuff has the same read on this. N cubed says that the endpoints will not be included, just like before. The x minus 2 to the n is telling us that the center is at 2. But now I don't just have a 10 to the n in the denominator telling me a radius is 10. We also have a 4 to the n in the numerator. So our radius is going to be 10 over 4. So we're going to look at all the exponential stuff. All the constant exponential stuff, and say that our radius will be 10 over 4. 10 from the denominator, 4 from the numerator. So when we draw our interval of convergence, In the middle, we still have 2, but now we're going to have a radius of 10/4 or 5/2 or 2.5. So we're going to go up 2.5 to 4.5 and down 2.5 to -1/2. The rational radical part indicates that the endpoints will not be included. We always get the center because that zeroes out all the terms. And then the exponential stuff has given us this radius. So just go from -0.5 to 4.5 in interval notation. This is from -0.5 less than x less than 4.5. Because the endpoints are doing the same thing, we could describe this as an absolute value inequality. Absolute value of x minus 2 has to be less than 2.5. We would interpret that as saying everything within 2.5 units of 2, which is everything between -0.5 and 4.5. Remember that this absolute value inequality, less than some tolerance, is what we use way back in the day when we wrote down the precise definition of a limit. This is how we wrote down the precise definition of a limit. This is so we can get over the kind of hand-wavy definitions of things like continuity and start saying precisely what we mean in a useful and rigorous fashion. But the definition of limit says the limit as x approaches c of f of x equals L if and only if for every epsilon greater than 0, there's a delta greater than 0, such that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. That is to say, for any tolerance that you choose, for any epsilon, that's your tolerance, that you choose, we can find some other tolerance delta. So every time you choose an epsilon, did I point right? I aimed wrong. I can't see that far. For every epsilon greater than 0, this is the tolerance that you choose. We can find every tolerance that you choose for the function, we can find a tolerance for x such that so long as x is within delta units of c, f of x will be within epsilon units of L. For every tolerance you choose for the function, we can find a tolerance for x such that x is within, if x is within delta units of c, if x is within delta units of c, then f of x will be within epsilon units of L. We can get f of x as close as we want to L, so long as we make x sufficiently close to C. And we write that in absolute value inequality notation, because that's how we say, I want to be within this radius of this spot. We can write down these absolute value inequalities in another way. We could say if x is strictly between C plus delta and C minus delta, then f of x will be between L plus epsilon and L minus epsilon. If we had believed what we had been taught in algebra, where we always have to simplify or remove our absolute value inequalities and write a compound inequality, this is how we would have written the definition. Earlier, I had mentioned balance. So the only way to balance out this exponential is with another exponential. If I had raised the exponent on this n cubed, if I had to replace that with n to the 10th, same result. Doesn't affect the radius. If I had written it as n to the 100th, same result. Endpoints not included. It's only telling us about the endpoints. The only thing that will balance out the exponential factor is another exponential factor. The same is true with factorials. If we have multiple factorials in our factor, then those might balance out. So let's take a look at an example. So yesterday we looked at an example where we had an x to the n over n factorial. And we saw that this converged for all x. The n factorial left behind 1 over n plus 1 in the limit from the ratio test. So when n went to infinity, the terms went to 0 regardless of the value of x. So if I try to balance this n factorial out with some other factorial, I knew I was going to be writing something here. I didn't leave enough space, so I'll have to write it small. I'm going to throw some other factorial. So now we have factorials that might balance each other out. Everything else, once these show up in the numerator and a factorial shows up in the denominator, nobody else needs to show up. Whatever else I throw in there, doesn't matter. The factorials are going to be dominating the conversation. I could put a 10 to the n in the denominator, factorials don't care. I could put a 100 to the n up in the numerator, factorials don't care. We've got a 2n factorial over an n factorial. Those are going to be our primary focus. That's going to take all of the attention. This is like if you're playing in your high school band and you're in the high school band concert and everybody's like focused on you. And all your friends are there to see you perform in your high school band. And then fucking Jay-Z walks out on the stage and Beyonce. And all your friends are like, oh, well, we were paying attention to them. You just became rational/radical in that situation because Jay-Z and Beyonce are the exponential. And all the events are supposed to be on them. Then, of course, your parents are there, and they're like, oh, who are these people? You must be somebody who's popular. And all the parents still paying attention to you. And then the Grateful Dead walked out onto the stage, including the ghost of Jerry Garcia. And now your parents are done. You're only going to be relevant at the endpoints because you are rational and radical. So after the show is over, your parents and your friends are going to say, hey, you did great, but they did not pay attention to you. So I'm just going to include the Grateful Dead, including the ghost of Jerry Garcia on the stage. Anything else is going to be dominated by that part of the conversation. All right, so let's see how these interact. I've got a combination of factorials. So let's use a ratio test and see how those interact. One of the things that we want to remember in the ratio test, an n factorial is going to leave behind a factor of n plus 1. The 2n factorial is going to leave behind 2 factors of n. This is what we want to eventually conclude so that we don't have to write this down. But let's write it down anyway. We'll take the limit as n goes to infinity of the absolute value of an plus 1. The tricky part about the 2n factorial is that the n gets turned into an n plus 1. Then we multiply by 2, then we factorial. So just replace the n with an n plus 1 all the way through for your an plus 1. So here we have an x to the n plus 1. The x to the n plus 1 knows what's up. It's like, oh, all these factorials running around, I'm just kind of an exponential part of this whole thing. I'm going to get ignored. And then we're going to multiply by 2n factorial, x to the n, and in the numerator, and n factorial. So instead of dividing by an, I'm going to multiply by the reciprocal of an because that's the same thing, and I want to save vertical space. Now we start the cancellation process. Remember, we cancel like with like. The x to the n plus 1 and the x to the n, that simplifies to an absolute value of x. It super works out because that'd be like the middle child, and we know the middle child always gets ignored, right? It's like, oh, well, I'm going to matter with all these Marcias running around. So our strategy for dealing with factorials is to write the bigger factorial until we get to the smaller factorial. Always compare the like with like. The n plus 1 factorial and the n factorial. That's where we want to start canceling things out. So that's the n factorial canceling out and leaving an n plus 1 in the denominator. But in the numerator, we've got a 2n plus 2 factorial. So it's an n plus 1, then times 2, and then factorial. So this up here is a 2n plus 2 factorial. So because it's a 2n plus 2 factorial, the smaller factorial, the 2n factorial, is 2 steps down, 2 factors down. We write the bigger factorial until we get to the smaller factorial, and that's what cancels out. So what's left behind from the 2n factorial is 2 factors of n, a 2n plus 2 and a 2n plus 1. We've seen this happen before, but it bears repeating. So now, when n goes to infinity, the x is like, oh, well, I never mattered in the first place because of all these factorials running around. In the numerator, we have an n squared. In the denominator, we have just an n. And so the numerator wins. This limit goes to infinity. And although it's weird to say, infinity is bigger than 1. I wouldn't want to write is greater than 1 because we can't really put infinity in equations and inequalities like that, but certainly we're going to get something bigger than 1. So the ratio test says divergence. Therefore, this power series only converges when x equals 0. So in this case, we had a factorial in the denominator and a factorial in the numerator, but we had a bigger factorial. We had more factorial in the numerator. So in the previous example, the radius of convergence was 0 with a center of 0. I don't want us to conflate those two things. This example just shifts 3 units to the right. The 2n factorial is much more powerful than just one n factorial in the denominator. So we'll have our interval of convergence of just 3. Here, the radius of convergence is 0 because that 2n factorial leaves behind two factors of n in the numerator, but the n factorial leaves behind one factor of n in the denominator. So the limit from the ratio test is off to infinity. We didn't have enough factorial to balance stuff out. Clearly, what we need is more factorial. Now, if we were to think about what happens in the ratio test, we're going to run the ratio test in a minute, but we want to think about what happens. We want to know what's going to happen before we start doing stuff. In the numerator, in the ratio test, we're going to have that 2n factorial is going to leave behind a 2n plus 2 and a 2n plus 1. In the denominator, the n factorial is only going to leave behind an n plus 1. But now I've got an extra factor of n plus 1 factorial. That's going to leave behind an n plus 2. 2 n's in the numerator, 2 n's in the denominator. This is going to balance out. It's going to balance out, and our radius of convergence is going to be 1/4. Let's do the ratio test and find out. So we'll do absolute value of a 2n, the an plus 1. Remember, in a 2n factorial situation, that's 2 times n plus 1 in parentheses, factorial. It's add 1, then multiply by 2, then factorial. That's the order of operations there. X minus 3 just becomes an x minus 3 to the n. In the denominator, n factorial is going to become an n plus 1 factorial. The n plus 1 factorial is going to be an n plus 2 factorial. And then we're going to multiply by the reciprocal of an. So I have a 2n factorial and x minus 3 to the n under an n factorial and an n plus 1 factorial. Now we're ready to squid game some of these factors, cancel some stuff out. We want to cancel like with like. The things that came from the same spot. The x minus 3 to the n over to the n plus 1, I forgot the plus 1, this one tried to trick me and escape, is going to leave behind an absolute value of x minus 3. We're not sure that this is going to matter with all these factorials running around. I'm going to cancel out whatever came from the 2n factorial. So the 2n plus 1 factorial, that's going to be 2n plus 2 factorial. We're going to write the big one until we get to the small one. So it's going to be 2n plus 2 times 2n plus 1 times 2n factorial. And that's the one that cancels out. So what's left behind in the numerator is a 2n plus 2 and a 2n plus 1. So the numerator is like, oh, I have brought 2 factors of n. You cannot possibly balance this out. But in the denominator, I've got this n plus 1 factorial. I'm going to write that one until we get to the smaller one. So it's n plus 1 times n factorial, and then the n factorials cancel out. So we're left with an n plus 1. And things are looking dire for our denominator. This is the same situation we were in the last problem. But there's this n plus 2 factorial. I'm going to write that one until we get to the smaller. N plus 2 times n plus 1 factorial. And then the n plus 1 factorial cancels out, but it left behind an n plus 2 in the denominator. So now up in the numerator, I've got a 4n squared, and in the denominator, I've got an n squared. So we're going to get a finite radius of convergence. Let's just focus on the important terms so I don't have to multiply things out. There's a 4n squared plus some stuff, and then the denominator n squared plus some other junk. Now, as n goes to infinity, the limit from the ratio test is 4, absolute value of x minus 3. So here, the factorial is balanced out. And we ended up with a positive finite radius of convergence. It was looking pretty dire when we had that 2n factorial in the numerator. It's like, oh, I'm going to dominate everything. Looks at the n factorial. It's like, oh, you can't do anything to hurt me. I am a 2n factorial. I leave behind 2 factors of n. And meanwhile, n factorial is like, oh no, what are we going to do? Then n plus 1 factorial shows up. And it's Vin Diesel in the charge. It's like, well, you're going to rely on family. And then they balance each other out. It's important that they balance each other out and not kill each other off so that 2n can become part of the team in the next movie. Fast and Furious 11. Fast and Furious takes over the MCU. I don't know if I mentioned this before, but the Fast and Furious is like the greatest movie franchise of all time. The MCU can suck eggs. I love the MCU, but I mean, it's no Fast and Furious. And I also want to point out that when Fast 5 came out, I told all my friends, these are the greatest movies of all time. This right here, this is American mythology. And I said, you realize by Fast and Furious 10, they're going to be in space. And they're like, oh, dude, you were wrong. They were in space in Fast and Furious 9, right? But what did we forget about? Fast and Furious, Hobbs and Shaw. Fast and Furious 9 was the 10th movie. They're going to be off by 1 for forever. But when the number actually reaches 13, it'll be Fast and Furious. Jason takes the 4th mile. All right. At a certain point, the cast is going to be bigger than the MCU anyway, because all the villains just become heroes. all the village was joined. I think I might be in one of these movies at some point. That would be awesome. They're going to need some kind of integration to be done. We need some integration done off the grid. And Dominic Toretto's going to be like, oh, I don't want that. Then I'm going to cut the movies in the classroom. And I'm going to be in. So we can see that the important part of the balance came from the fact that there were two factorials to balance out the end. It's like, oh, hang on, everybody. And Dominic, because it's didn't even be like walking the class. I mean, oh, what's up? It's like, oh, we need integration stuff. Like, I gotta go. And, and because it's Fast and Furious, we would all get in separate cars and be driving out of the Skyline parking lot. I'm just kidding. Vin Diesel will not show up. I'm not allowed to call him anymore. Stupid restraining order. I'm just kidding. I don't have a restraining order. Vin Diesel does not have a restraining order. It expired, but I think he's going to be it. I'm just kidding. I'm not stalking Vin Diesel. Maybe what my lawyer said I have to say. I'm just kidding. I don't have a lawyer. I represent myself. I'm just kidding. So the interval of convergence is going to, the ratio test says we get convergence if this limit from the ratio test is less than 1. As usual, we solve for the absolute value factor. And this tells us that the absolute value of x minus 3 has to be less than 1/4. So in the center, we have a 3. Down below, we've got a 2 3/4. And up above, we have a 3 1/4. Since the only thing going on in this example are these factorials, the ratio test says we don't know what's going on at the endpoints. At the endpoint, one endpoint is a 1 to the n. At the other endpoint is a -1 to the n. Both diverge. So our interval of convergence is 2 3/4 to 3 1/4. That means x is going to be greater than 2 3/4, but less than 3 1/4. Since the inequalities are the same, both endpoints are doing the same thing. We can just say this is everything within 1/4 unit of 3. But we've discovered a situation where the factorials are balancing out. So it might become relevant to look at what's going on with the exponential factors. So initially, when we look at this, we see all these factorials running around and say, oh, this x minus 3 to the n is not going to matter. This 7 to the n is not going to matter. But then we notice that there's a 2n factorial in the numerator and 2 different n factorials in the denominator. That's going to cause a balance. That's going to give us the 4, just like in the previous problem. But now we've got a denominator of 7. So our limit from the ratio test is going to be 4/7 times the absolute value of x minus 3. Making that less than 1 is going to tell us the absolute value of x minus 3 should be less than 7/4. So this will be everything within 7/4 of 3. So in the middle, we'll put our 3. up at the top, we'll put 3 and 7/4. And at the bottom, we'll put 3 and -7/4. These don't actually look like how we would write these numbers because it's not how we would write these numbers. We don't say 3 and 7/4. We don't combine our improper fractions and our mixed numbers, but we can fix it in the same way that we always do. 3 times 4, 4 times 3 is 12. 12 plus 7 is 19. So we'll call this 19/4. And over here, we'll fix it in the exact same way. 4 times 3 is 12. 12 minus 7 is 5. So this is going to be 5/4. That way we're writing the numbers in the normal way, not some weirdo 3 and 7/4 way. Saying something like 3 and 7/4 is saying something like 2012 when you mean 3. I've always thought that we should introduce a little bit of flexibility into how we describe things. Because we count base 10 and it's so boring. And we tell kids they're wrong when they say that's 2012. But 2012 is 20 and 12 is 32. 32 is a common name. Anyway, I digress. Any questions? Think about balance, numerator and denominator. Think about factorials dominating over exponentials, dominating over rational and radical. We have seen this very niche example where the 2n factorial was balanced by 2 different n factorials. Another way that you'll see this balanced out is, say, a 2n factorial over an n factorial squared. Now notice that notice the order of operations down here. Down here, first we factorial, then we square. So this is going to have the same balance as an n factorial and an n plus 1 factorial. Also notice that I had to go all the way up to a 2n factorial to balance things out. If I had in the denominator an n factorial and I tried to balance it out with just an n factorial, or say an n plus 1 factorial, these balance out too much because this should just be simplified. N plus 1 factorial over n factorial is just n plus 1 times x to the n. So when we have n factorial divided by n factorial, we don't actually have factorials running around. It's a false factorial. Simplify that in just n plus 1. This n factorial or n plus 1 factorial or n factorial is when you have a player whose character is going to be 3 kobolds in a trench coat. That player should just be all 3 kobolds. It's going to be part of the disguise, right? It should be 3 different players that want to play 3 kobolds in a trench coat. Unless your party consists of 3 players that want to be 1 character that is 3 kobolds in a trench coat. I don't know. Your group does your group. What I'm saying is that n plus 1 factorial over n factorial, that should be simplified because it's not really factorial. Any questions? Comments? Snide remarks? I think I heard there is a fact. And are they just going to call it fast X? And is it going to be pornographic? I don't think anybody needs to see that. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day. Thanks. Bye.